Good evening and welcome. Some nights the stars feel closer than they should. The air grows still. Time slows just enough for the mind to ask questions it usually doesn't have room for. Tonight is one of those nights. Picture this. A young man sits by a window in Bern, Switzerland, watching the clock tower across the street. The year is 1905. He works at a patent office examining other people's inventions during the day. But at night, his mind drifts towards something bigger. He imagines himself running alongside a beam of light faster and faster until he's moving at the same speed as the light itself. And then he wonders, if I could run that fast, would the light beside me appear frozen? Would it stop moving altogether? That question, so simple, so strange, would change everything we thought we knew about the universe. Before we begin this quiet journey together, if you find peace in stories like these, you might like to stay a while. You can gently tap the like button, subscribe if you would like, more science told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. Tonight we are going to explore something both invisible and absolute, the hidden structure of space-time, and why the universe has a speed limit at all. Not a rule written by anyone, not a boundary someone drew, but something woven into the fabric of reality itself. A limit so fundamental that without it cause and effect would unravel, stories would have no order, and time itself would lose all meaning. You don't need to understand everything. Just rest and let curiosity do the listening. The man by the window was Albert Einstein, and his question about light wasn't just playful imagination. It was the beginning of a revolution. Because in 1905, the scientific world believed that light traveled through an invisible medium called the ether, a substance that filled all of space like water fills the ocean. If light needed the ether to move, then someone traveling fast enough might catch up to a light wave and see it standing still, the way you might see ripples frozen on a pond if you moved with them. But Einstein had read about an experiment. Two scientists, Albert Michelson and Edward Morley, had tried to detect this ether in 1887. They built an interferometer, a device so sensitive it could measure the tiniest shifts in light waves. They reasoned that if Earth was moving through the ether, light traveling in the direction of Earth's motion should move slightly slower than light traveling perpendicular to it, the way a swimmer moves slower when swimming upstream. But they found nothing. No difference. No ether wind. Light moved at the same speed in every direction, no matter how Earth was moving. It was as if the universe had shrugged and said, "There is no medium. Light doesn't need one." Scientists were baffled. Some suggested the Earth dragged the ether along with it. Others proposed that objects shrink in the direction of motion, perfectly canceling out any measurable effect. But Einstein looked at the result and thought differently. What if he wondered the speed of light isn't relative? What if it's always the same, no matter who's measuring it or how fast they're moving? It sounds absurd at first. If you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the platform sees the ball moving at 80 miles per hour. Speeds add. That's common sense. But light, Einstein realized, doesn't follow that rule. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, someone standing still doesn't see the light moving at 1.5 times the speed of light. They see it moving at exactly the speed of light, the same speed you see. This is where the universe begins to feel strange, because if the speed of light is always the same, then something else has to give. And what gives is time and space. They stretch, they shrink, they bend to keep light's speed constant. Einstein called this special relativity, and it meant that the universe wasn't a stage where events played out against a fixed backdrop of space and time. Space and time were part of the performance. They were flexible, responsive, woven together into a single fabric space-time. The speed of light, about 299,792,458 meters per second, often rounded to 300,000 kilometers per second, wasn't just the speed of light. It was something deeper. It was the speed of causality itself, the speed at which cause and effect could travel, the maximum speed at which information influence or change could move from one place to another. Think of it this way. Imagine you're standing in a dark room and someone across the room flips a light switch. The light doesn't reach you instantly. It travels. It takes time. Not much time light crosses a room in billionths of a second, but time nonetheless. And during that tiny interval, there's a separation between the cause, the flipping of the switch, and the effect the light reaching your eyes. Now imagine that separation couldn't exist. Imagine effects happened instantly everywhere the moment a cause occurred. The past and future would collapse into each other. There would be no sequence, no story, no way to say, this happened and then that happened. The universe would be a blur of simultaneous everything. The speed limit, this cosmic constant we call c, is what keeps that from happening. It creates distance and time. It ensures that every event has a before and an after. It protects the order of things. But here's the part that feels almost personal. Nothing with mass can reach that speed. Not spaceships, not particles, not you. Only light and things like light massless things can move at c. Everything else is bound to move slower. Not because of friction, not because engines aren't strong enough, but because the universe itself resists it. And this resistance isn't a wall you hit. It's subtler than that. The faster you move, the more energy it takes to go even faster. And as you approach the speed of light, the energy required grows without bound. You'd need infinite energy to reach it, which means you never can. Scientists have tried. At CERN, the Large Hadron Collider accelerates protons to 999,999,991% the speed of light. That last tiny fraction of a percent, the difference between 99.9999991 and 100, requires as much energy as everything before it. The closer you get, the harder it becomes. Not because the machine isn't strong enough, but because space-time itself pushes back. From the outside, it looks like a speed limit, but from the inside, it feels more like a truth you can't outrun the structure of reality. Let's sit with that for a moment. The universe has a pace. Not a slow pace, not a fast one, but the pace. The speed at which change moves, the speed at which now becomes then. And every star, every atom, every thought you've ever had moves within that rhythm. Einstein didn't discover this limit to control us. He discovered it because it was always there, hidden in the way light behaves, in the way time flows differently for a person standing still and a person in motion, in the way the universe holds itself together. Some people find this comforting. The idea that there's a structure beneath the chaos, a speed woven into the fabric of everything, a reason why the past stays in the past and the future waits ahead. Others find it frustrating. Why should there be a limit at all? Why can't we go faster? See farther, reach further. But maybe the question isn't why the limit exists. Maybe it's what the limit protects. What would we lose if there were no maximum speed? If information could travel infinitely fast? If cause and effect could happen in the same instant? If there were no space-time to stretch or curve or bend? We'll drift into that question soon. But first we need to understand what space-time actually is. Not the metaphor, not the analogy, but the thing itself. Because space isn't empty. It never was. And time isn't a river flowing in one direction. It's stranger than that. More flexible, more real. The young man in Bern looked at a clock tower and imagined light. And in doing so, he glimpsed something most of us never see: the hidden geometry of existence. The scaffolding, beneath motion, beneath distance, beneath now. Let's follow him further. Let's step into the fabric. The question Einstein asked wasn't just about light. It was about what light reveals. Because if light always moves at the same speed, then the universe must be doing something extraordinary to keep it that way. And what it's doing is reshaping space and time themselves moment by moment to preserve that constancy. We've been taught to think of space as nothing, a void, an absence, the empty stage where planets spin and stars burn. But what if space isn't empty at all? What if the thing we call nothing is actually the most fundamental something in the universe? Close your eyes for a moment and picture the room around you. Now, imagine removing everything: the walls, the air, the light, even the atoms. What's left? Most people would say nothing. But that's not quite right. What's left is space-time. And space-time is not nothing. It's a fabric, a structure, a field that can bend, stretch, ripple, and even tear. This isn't poetry, it's physics. And it took centuries to understand. In the late 1800s, scientists believed that light-like sound needed a medium to travel through. Sound moves through air, through water, through solid ground. So, light, they reasoned, must move through something too. They called it the luminiferous ether, an invisible weightless substance that filled all of space, allowing light waves to propagate across the cosmos. It seemed reasonable. After all, if light is a wave, what is it waving? Two men decided to test this idea directly. Albert Michelson, a physicist, and Edward Morley, a chemist, built one of the most precise instruments of their time, an interferometer. The device split a beam of light into two perpendicular paths, bounced them off mirrors, and recombined them. If Earth was moving through the ether, the light traveling in the direction of Earth's motion should take slightly longer to return than the light traveling perpendicular to it, like swimming upstream versus across a river. They conducted the experiment in 1887 in Cleveland, Ohio, in a basement to minimize vibrations. They measured, recalibrated, measured again, and found nothing. No difference in the speed of light no matter which direction it traveled. No trace of the ether. Scientists were stunned. Some proposed elaborate explanations. Maybe the Earth dragged the ether along with it like a ship dragging water. Maybe objects contracted in the direction of motion, perfectly compensating for the ether wind. But none of these explanations felt right. Einstein looked at the results and saw something else. What if there is no ether? What if light doesn't need a medium because space itself is the medium? This was the beginning of a radical shift. Space wasn't a container. It wasn't a backdrop. It was a participant, an active, dynamic thing, and it wasn't separate from time. The two were fused together into a single four-dimensional fabric space-time. Imagine a trampoline stretched tight. Now, place a heavy ball in the center. The surface curves, dips, creates a valley. That's what mass does to space-time. It bends it. And that bending is what we experience as gravity. But here's the part that feels almost impossible to grasp. Space-time isn't in the universe. Space-time is the universe. Every point in space, every moment in time is a coordinate on this fabric. When you move through space, you're moving through space-time. When time passes, you're traveling along a path through this four-dimensional geometry. Scientists call this a metric, a mathematical way of measuring distances in space-time. In flat, empty space, far from any mass, the metric is simple, described by something called Minkowski space-time. But near a star, near a planet, near anything with mass, the metric changes. Distances stretch, time dilates, the fabric curves. In 1915, Einstein published his theory of general relativity, which described how mass and energy curve space-time and how that curvature dictates the motion of objects. He wrote it as a field equation: G mu nu equals 8 pi g over c to the fourth power T mu nu. On the left side, the curvature of space-time. On the right side, the distribution of mass and energy. They're equal. Mass tells space-time how to curve. Space-time tells mass how to move. It's elegant. It's beautiful. And it's been tested over and over again in laboratories and observatories, in the cosmos itself. But let's step back from the equations and think about what this means for the speed limit. If space-time is a fabric, then nothing can move through it faster than the fabric itself allows. And the maximum speed, the speed of light c, is built into the structure of space-time. It's woven into the metric. It's part of the geometry. Think of it like this. Imagine you're walking on a surface that can stretch. The faster you try to move, the more the surface stretches beneath your feet, resisting your motion. You can walk faster, run faster, but there's a point where the surface stretches so much that you can't gain any more ground. That's what space-time does. It resists motion, and the resistance becomes infinite as you approach the speed of light. This is why the speed limit isn't arbitrary. It's not a rule imposed from outside. It's a consequence of the way space-time is built. And because space-time is what reality is made of, the speed limit is as fundamental as existence itself. Now, here's something subtle that most people miss. Space-time isn't the same everywhere. Near a massive object, space-time is curved. Time runs slower. Distances stretch. This means the speed limit isn't just about velocity through space. It's about how you move through space-time as a whole. Imagine two paths between the same 2 points. One path goes through flat, empty space. The other goes near a black hole. The path near the black hole is curved, stretched, warped by gravity. Even if you travel at the same speed along both paths, the journey through curved space-time takes longer. Not because you're moving slower, but because space-time itself is different there. This is what GPS satellites experience every day. They orbit Earth at about 20,000 kilometers above the surface, moving through slightly less curved space-time than we experience on the ground. To them, time runs faster, about 38 microseconds per day, faster. If GPS satellites didn't account for this, your navigation would be off by kilometers within a single day. Let's pause here and think about what this means for the universe. Space is not a void, it's a structure. It has properties. It can be measured, it can be bent. It can even ripple like the surface of a pond, creating gravitational waves that travel at the speed of light. In 2015, scientists detected gravitational waves for the first time, using an observatory called LIGO. Two black holes billions of light years away had collided and merged, sending ripples through space-time. Those ripples traveled across the universe, stretching and compressing space itself, as they passed until they reached Earth and caused the arms of the detector to shift by a distance smaller than the width of a proton. The detection proved something profound. Space-time is real. It's not just a mathematical abstraction. It's a physical thing that can vibrate, that can carry energy that can be measured. And if space-time can ripple, it can also be torn. Near the center of a black hole, space-time curves so sharply that it breaks. The fabric doesn't just bend, it folds in on itself, creating what physicists call a singularity, a point where the curvature becomes infinite and the laws of physics as we know them stop working. But we'll come back to that. For now, the key thing to understand is this: space-time is not passive. It's not just a stage. It's active, responsive, alive in its own way. And the speed of light is the speed at which changes propagate through this fabric. When you flip a light switch, the electromagnetic field around the switch changes, and that change ripples outward through space-time at the speed of light. When the sun suddenly vanished, hypothetically, of course, Earth wouldn't feel the loss of gravity instantly. The change in the gravitational field would travel outward at the speed of light, taking about 8 minutes to reach us. Cause and effect, action and consequence are bound by this speed. Not because the universe is slow, but because space-time has a structure, and that structure has a maximum rate of information transfer. Think of it like the refresh rate of existence. The universe updates at the speed of light. Anything faster would violate the geometry. It would be like trying to draw a triangle with 4 sides. It's not that it's hard, it's that it's impossible within the rules of the system. Some people wonder, couldn't there be a different space-time somewhere with a different speed limit? Maybe, in theory, if the fundamental constants of nature were different, space-time might permit faster or slower propagation of causality. But in our universe, with our physics, C is what it is. And everything else follows from that. Here's a question worth sitting with. If space-time is a fabric, what is it made of? What lies beneath the geometry? Physicists don't know yet. Some think space-time is fundamental, the most basic thing there is. Others think it might emerge from something deeper: quantum fields, entangled particles, information itself. The search for an answer is one of the great puzzles of modern physics. But even without knowing what space-time is made of, we know what it does. It connects every event in the universe. It separates the past from the future. It creates the distance between here and there, between now and then. And it enforces the speed limit not as a constraint, but as a feature, a rhythm, a pace that keeps the universe coherent. So, when we talk about the speed of light, we're really talking about the speed of space-time, the speed at which the fabric of reality can change, the speed at which being flows into becoming. And nothing, no matter how much energy you pour into it, no matter how advanced the technology, can move faster than the structure of existence itself. But what happens when something tries? What does it feel like to approach that limit? And why does the universe resist so strongly? There's something you need to understand about light, something so strange that even physicists sometimes pause when they think about it too carefully. From the perspective of a photon, a particle of light, the journey from the surface of the sun to your eye takes no time at all. 0 seconds, no duration. The moment it leaves the sun and the moment it touches your retina are, for the photon, the same moment. How can that be? How can something travel 150 million kilometers and experience no time? The answer lies in the geometry of space-time itself. And once you see it, the speed limit stops feeling like a restriction and starts feeling like a window into the deepest nature of reality. Let's begin with a thought experiment. Imagine you're standing still and I'm moving past you at half the speed of light. We both have clocks. To you, your clock ticks normally 1 second, 2 seconds, 3. But when you look at my clock, it appears to be running slow. Not because it's broken, but because time itself is passing more slowly for me relative to you. This isn't an illusion. It's not a trick of perception. Time actually runs slower for objects in motion. This effect is called time dilation, and it's been measured thousands of times in laboratories and in nature. In 1971, 2 physicists named Joseph Hafele and Richard Keating conducted one of the most famous tests of time dilation. They took 4 cesium atomic clocks devices so precise they lose only 1 second every 100 million years and flew them around the world on commercial airplanes. 2 clocks flew eastward moving with Earth's rotation. 2 flew westward against it. When they returned and compared the airborne clocks to identical clocks that had remained on the ground, they found the traveling clocks had gained and lost time exactly as Einstein's equations predicted. The eastward clocks moving faster relative to Earth's center had lost 59 nanoseconds. The westward clocks had gained 273 nanoseconds. 59 billionths of a second, measurable, real. Now, the faster you move, the stronger this effect becomes. At 90%, the speed of light time for you passes at about 44%, the rate it does for someone standing still. At 99% time, slows to about 14%. At 99.9%, less than 5%. And at the speed of light itself, time stops. Completely. This is described mathematically by the Lorentz transformation, a set of equations that relate measurements of time and space in one reference frame to measurements in another. The key term is a factor called gamma gamma equals 1 over the square root of 1 minus v squared over c squared. As velocity v approaches the speed of light, c, the denominator approaches 0 and gamma approaches infinity. Time dilation becomes total. For a photon moving at exactly c gamma is undefined. Time as we experience it doesn't exist for light. Let's make this concrete. Imagine a photon is born in the core of the sun. It's created in a fusion reaction deep in the roiling plasma, where hydrogen nuclei slam together to form helium-releasing energy. That photon begins a long, chaotic journey outward, bouncing off particles scattering, absorbed, and re-emitted countless times, taking something like 100,000 years to reach the sun's surface. But once it breaks free, once it escapes into the vacuum of space, it travels in a straight line toward Earth. 8 minutes and 20 seconds later, by our clocks, it enters your eye, strikes a cell in your retina, triggers a cascade of chemical reactions, and becomes part of a signal your brain interprets as sunlight. From our perspective, that journey took 8 minutes. But from the photon's perspective, if we could somehow ride along with it, experience what it experiences, the departure from the sun and the arrival at your eye happen in the same instant. No time passes. The universe along the photon's direction of travel is compressed to zero length. The sun and your eye are in the same place. This is what physicists mean when they say light doesn't experience time. It's not a metaphor, it's geometry. Now, here's where it gets even stranger. Photons aren't the only things that experience this. Any particle moving at the speed of light, and there are a few, all of them massless lives in this timeless state. Gluons, the particles that hold quarks together inside protons and neutrons, move at c. Gravitons, if they exist, would move at c. All of them exist in a kind of eternal now. But everything with mass electrons, protons, atoms, molecules, dust planets, stars, you cannot reach this state. We are bound to experience time. We are bound to move slower than c. And the reason has to do with something called proper time. Proper time is the time measured by a clock that's moving with you. It's your personal experience of duration. When you move through space-time, you're always moving at the speed of light through space-time. But that motion is divided between motion through space and motion through time. If you're sitting still in space, all your motion is through time. You experience time passing at its maximum rate. But if you start moving through space, some of that motion gets redirected. You move through time more slowly. Think of it like a budget. You have a fixed total amount of motion through space-time. You can allocate it however you want between space and time, but the total is always c. If you're not moving through space, all of it goes into time. If you start moving through space, you have to borrow from your time budget. The faster you move through space, the slower you move through time. Light uses its entire budget for motion through space. None left for time. This is why photons are eternal, in a sense. They don't age, they don't decay. A photon created in the Big Bang 13.8 billion years ago is still from its own perspective being created. It hasn't experienced a single moment since then. Now, let's talk about something that seems impossible but happens constantly. Particles that shouldn't reach Earth but do. High above the atmosphere, cosmic rays, high-energy particles from space collide with atoms in the upper air, creating showers of secondary particles. Among them are muons, unstable particles that exist for only about 2.2 microseconds before decaying into other particles. That's their half-life, 2.2 millionths of a second. The upper atmosphere where these muons are created is about 10 kilometers above sea level. Even if a muon were traveling at the speed of light, it would take about 33 microseconds to reach the ground. But the muon only lives for 2.2 microseconds. It should decay long before reaching the surface. And yet, muons reach the ground all the time. Detectors at sea level register them constantly. How? Time dilation. The muons are moving at about 98% the speed of light. From our perspective, their internal clocks run slow. What feels like 2.2 microseconds to the muon stretches to about 15 microseconds for us. Plenty of time for them to reach the ground. From the muon's perspective, something else is happening. It doesn't experience our 15 microseconds. It experiences only 2.2. But from its point of view, the distance to the ground isn't 10 kilometers. Length contraction. Another consequence of relativity compresses the distance to about 1.4 kilometers. So, the muon living its brief 2.2 microseconds covers a much shorter distance and reaches the ground just fine. Two perspectives, both correct, both necessary to describe the same event. This was first observed in 1941 by Bruno Rossi and David Hall, who placed detectors on a mountain and at sea level and measured the number of muons arriving at each location. The math worked perfectly. Time dilation and length contraction were real. But here's the thing that keeps physicists awake at night. Why is c the speed that it is? Why 299,792,458 meters per second and not some other value. Is it arbitrary or does it follow from something deeper? We don't know. The speed of light is a fundamental constant. It appears in equations all over physics, electromagnetism, relativity, quantum mechanics. It seems to be woven into the structure of the universe at the most basic level, but we can't derive it from first principles. We can only measure it. Some physicists suspect that CE isn't really about light at all. It's about causality. It's the speed at which cause and effect can propagate through spacetime. The fact that light travels at this speed is almost incidental. Light just happens to be massless, so it reaches the universal speed limit. Gravitational waves also travel at c, so do gluons. So would any massless particle. The commonality isn't light, it's the absence of mass. Mass, it turns out, is what slows things down. Or more precisely, mass is what forces things to experience time. And experiencing time means moving slower than c. There's a beautiful symmetry here. Massless particles move at c and don't experience time. Massive particles experience time and can't reach c. The two are connected two sides of the same coin. But why does mass have this effect? Why does having mass mean you must experience time? The answer lies in something called the Higgs field, a field that permeates all of space. Particles that interact with the Higgs field acquire mass. Particles that don't interact with it remain massless, and the strength of that interaction determines how much mass a particle has. But the Higgs field doesn't just give particles mass, it changes how they move through space-time. It forces them to experience time. It pulls them away from the speed limit. Photons don't interact with the Higgs field. They glide through it untouched, moving at c, timeless and eternal. Electrons interact with it weakly, gaining a tiny amount of mass, just enough to pull them into the flow of time. Quarks interact more strongly, gaining more mass, moving slower still. And you made of trillions of atoms, each containing particles that interact with the Higgs field, are deeply embedded in the passage of time. You cannot escape it. You cannot reach c. The Higgs field won't let you. So, when we ask why light doesn't need time, the answer is simple, because it has no mass. And when we ask why we do need time, the answer is just as simple, because we do have mass. The speed limit isn't a barrier keeping us from going faster. It's a boundary between two kinds of existence, one that experiences time and one that doesn't. And which side of that boundary you're on depends on whether you interact with the Higgs field. Light lives on the far side. We live here in time, where cause follows effect, where stories have beginnings and endings, where the universe unfolds moment by moment. But light doesn't see any of that. For light, everything that ever happens, happens now. And yet, light is the messenger. It carries information from the timeless realm into ours. Every photon that reaches your eye is a bridge between two ways of being. So when you look at the stars, remember the light you're seeing left those stars years, centuries, millennia ago by our clocks. But for the light itself, no time has passed. It is still leaving. It is still arriving. It is both at once. This is the paradox of C. It is the speed of timelessness, the speed of the eternal now, the speed at which the universe whispers its deepest secret, that time as we experience it is not fundamental. It's emergent, a consequence of massive interaction, of being something rather than nothing. And the closer we get to C, the closer we get to that timeless state, not by choice but by geometry, because space-time bends toward eternity as velocity rises. But there's a cost, and that cost is written into the very structure of motion itself. Imagine you could send a message faster than light. Just one message to anyone, anywhere in the universe, arriving before light could make the journey. It sounds harmless, doesn't it? Useful even. But that single message would shatter the logical structure of reality. It would allow you to change the past, to erase events that have already happened, to create paradoxes that have no resolution. The universe doesn't allow this, not because of a rule, but because of something deeper. The speed limit exists to protect causality itself. The principle that causes must precede their effects, that actions lead to consequences in a definite order. that the past stays fixed and the future remains open. Without causality, there are no stories, no sequences, no reason why anything happens at all. Let's explore why. In 1907, a mathematician named Hermann Minkowski gave a lecture that changed how physicists think about space and time. He said something remarkable. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What he meant was this: space and time aren't separate. They're woven together into a single fabric space-time, and every event in the universe is a point in this fabric. When something happens, a star explodes, a bird sings, a thought crosses your mind, it happens at a specific location in space-time. And the structure of space-time determines which events can influence which other events. This structure has a geometry, and at the heart of that geometry is a boundary called the light cone. Imagine you're standing at a point in space-time, let's call it here and now. From this point, light spreads outward in all directions, forming an expanding sphere. If you plot this sphere across time, it forms a cone. Everything inside that cone, every event that light from here and now can reach, is in your future light cone. Everything that can send light to you, everything that could have influenced here and now, is in your past light cone, and everything outside both cones. Those events are space-like, separated from you. They exist, but they can't influence you, and you can't influence them. Not yet. Not until enough time passes for light to travel between you. This is causality made geometric. Causes live in your past light cone, effects live in your future light cone, and the boundary between them, the surface of the light cone, moves at the speed of light. If nothing can travel faster than light, then nothing can escape the light cone structure. Every cause remains in the past. Every effect remains in the future. The order of events is preserved. But what if something could travel faster than light? What if you could send a signal outside your light cone into the space-like region? This is where things get strange, because in relativity simultaneity, the concept of now is not absolute. Events that appear simultaneous to you might not appear simultaneous to someone moving relative to you. This means that if you send a faster-than-light signal to someone, they might receive it before you sent it from their perspective. Let me give you an example. It's called the tachyonic anti-telephone, a thought experiment devised by physicists in the 1960s. Imagine two spaceships, Alice and Bob, moving away from each other at high speed. Alice at time zero. By her clock sends a faster-than-light message to Bob. From her perspective, the message is traveling into the future. But because Bob is moving relative to Alice, and because simultaneity is relative, Bob receives the message at what he considers an earlier time than Alice sent it. Then Bob sends a faster-than-light reply back to Alice. And because of the relative motion, Alice receives Bob's reply before she sent her original message. Alice gets Bob's response before she asks the question. The effect precedes the cause. The timeline loops back on itself. This isn't just a theoretical quirk. It's a logical impossibility. If Alice receives Bob's reply before sending her message, she could choose not to send it. But if she doesn't send it, Bob never receives it, so he never replies. So Alice never receives the reply that convinced her not to send the message in the first place. Paradox, contradiction. The breakdown of causality. The universe avoids this by making faster-than-light travel impossible. Not as a prohibition, but as a structural feature. The geometry of space-time simply doesn't allow it. Moving faster than light isn't like breaking the sound barrier where you just need more power. It's like trying to travel north of the North Pole. The question doesn't make sense within the framework of the system. Some people imagine that with enough energy, with advanced enough technology, we could find a way around this. They picture warp drives, wormholes, exotic matter. And in the mathematics of general relativity, these things are possible technically. You can write down solutions to Einstein's equations that allow faster-than-light travel without violating local physics. But every one of these solutions requires something that doesn't seem to exist: negative energy density or exotic matter, with properties never observed in nature. And even if such things did exist, the resulting spacetime would likely be unstable, collapsing before you could use it. The universe seems to conspire through a principle physicists call cosmic censorship to prevent violations of causality. Stephen Hawking once proposed a conjecture called the chronology protection hypothesis. It states half seriously that the laws of physics do not allow the creation of closed time-like curves paths through space-time that loop back to their own past. Hawking joked that this makes the universe safe for historians. But beneath the humor is a profound point. Causality isn't just convenient, it's foundational. Without it, physics breaks down. Prediction becomes impossible. The concept of a law of nature loses meaning because laws require consistency, and consistency requires that causes precede effects. Let's think about this from another angle. Suppose you could move faster than light. Not much faster, just a little. You send a beam of light from Earth toward a distant star, and then you follow it in a faster-than-light spaceship, overtaking the light along the way. You arrive at the star before the light does. Then you turn around and come back still faster than light, arriving on Earth before the light returns. From Earth's perspective, you've time traveled. You went to the star and returned all before the light made the round trip. But from the star's perspective, if there were an observer there, you arrived before you left. The sequence of events is different depending on who's watching. This is the heart of the problem. In relativity, the order of events can change depending on your reference frame, but only for events that are space-like, separated events that can't influence each other. For events that are causally connected, that can influence each other, the order is always preserved. Cause always precedes effect in every reference frame. Faster-than-light travel would break this. It would allow effects to precede causes depending on who's watching. And that would unravel the logical structure of space-time. Scientists have found this principle reflected in experiment after experiment. In particle accelerators, where particles are pushed to 99.9999%, the speed of light, researchers have never seen anything exceed c. Not once. Not by the tiniest fraction. In 2011, an experiment called Opera reported that neutrinos, ghostly particles that barely interact with matter, seemed to be traveling faster than light. The news was stunning. If true, it would overturn a century of physics. But physicists were skeptical. They checked the equipment, the methods, the calculations. And they found the error: a loose fiber optic cable and a faulty clock. Once corrected, the neutrinos were moving at exactly the speed you'd expect just below c. The universe held. Why does this matter? Why should we care that causality is protected? Because causality is what makes knowledge possible. It's what allows us to learn from the past, to predict the future, to understand that striking a match causes a flame, that planting a seed leads to a tree, that actions have consequences. Without causality, there's no science, no history, no memory. Just a chaotic soup of events with no connection, no pattern, no meaning. The speed limit is the guardian of this order. It ensures that information can only travel so fast that no signal can outrun the structure of space-time itself, that the past remains past, and the future remains future. Think of it this way. The speed of light is the refresh rate of the universe. It's how fast reality updates. Events propagate outward at c, stitching the present into the past, weaving the future from the now. And because nothing moves faster, the stitching holds. The fabric doesn't tear. Some physicists describe c as the speed of causality, not the speed of light. Light just happens to travel at this speed because photons are massless. But gravitational waves also travel at c. So does any influence, any interaction, any change that propagates through space-time. The commonality isn't light, it's causality. There's a principle in physics called locality, which says that objects are only directly influenced by their immediate surroundings. If you want to affect something far away, You have to send a signal, a particle, a wave, a field, and that signal can't travel faster than c. This keeps the universe local, keeps it causal, keeps it logical. Quantum mechanics seems to violate this sometimes. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he didn't like it. But physicists eventually proved that entanglement doesn't allow faster-than-light communication. You can't use it to send a message. The correlations are there, but they don't violate causality. Information still moves at c or slower. The universe is very careful about this, almost obsessively careful. Every loophole closes. Every potential violation turns out to be an illusion. And so, the speed limit stands not as a barrier, but as a foundation. It's what keeps time flowing in one direction, what keeps the past fixed, what allows the future to be unknown but not arbitrary. If you could break it, you wouldn't just go faster. You'd step outside the causal structure of reality. You'd become untethered from the flow of time. You'd exist in a space where effect and cause blur together, where logic unravels, where the universe stops making sense. And perhaps that's the deepest reason the speed limit exists, not to keep us from going too fast, but to keep the universe coherent, to preserve the difference between past and future, to make sure that stories can still be told, that consequences still follow from actions, that time still has meaning. So when we push against this limit, when we accelerate particles in colliders, or imagine starships cross in the galaxy, we're not just pushing against a speed, we're pushing against the boundary of comprehension itself. And that boundary pushes back, always. Because it's not made of force or energy. It's made of geometry, of logic, of the deepest structure of being, and you can't argue with that. You can only accept it, understand it, and marvel at how elegantly it holds everything together. But accepting the limit doesn't mean we're powerless. It means we're part of the structure. And understanding why the limit exists helps us see what motion really is, what energy really costs, and why the faster you try to move, the more the universe seems to weigh you down. Here's a question that sounds simple, but cuts to the heart of everything. Why can't you just keep accelerating? You're in a spaceship. You have unlimited fuel. You fire the engines, gain speed, fire them again, gain more speed. Why shouldn't you eventually reach the speed of light and then surpass it? The answer is as beautiful as it is strange. The faster you go, the heavier you become. Not heavier in the sense of gaining matter, but heavier in the sense that your inertia increases, your resistance to further acceleration grows, and the energy required to push you faster approaches infinity. The universe itself becomes an infinite wall, and it all comes down to the most famous equation in physics. In 1905, the same year Einstein published his paper on special relativity, he published another short paper, just 3 pages long. In it, he derived a relationship so fundamental that it would reshape our understanding of matter and energy. He showed that mass and energy are not separate things. They are two forms of the same thing related by a constant, the speed of light squared. E equals mc squared, energy equals mass, times the speed of light squared. It seems almost too simple, but embedded in those symbols is a profound truth. Mass is concentrated energy, and energy has mass. They are interchangeable two faces of a single coin, but there's more to this equation than most people realize. E equals mc squared is actually a special case, the energy of an object at rest. When an object is moving, the full equation is more complex. E squared equals mc squared squared plus pc squared, where p is momentum. And when you work through the mathematics, you discover something astonishing. The faster an object moves, the more energy it contains and the more inertia it has. This is called relativistic mass, though physicists prefer to talk about it in terms of energy and momentum now. The important point is this: as velocity increases, the energy required to accelerate further increases. Not linearly, but exponentially approaching infinity as you approach the speed of light. Let's make this concrete. Imagine you have a particle, a single proton. At rest, it has a certain amount of energy. Its rest mass energy about 938 million electron volts. Now you accelerate it to half the speed of light. Its total energy increases to about 1.08 billion electron volts. You've added about 15% more energy. Now accelerate it to 90% the speed of light. Its total energy is now 2.15 billion electron volts. You've more than doubled its energy, but you've only increased its speed by 40 percentage points. Push it to 99%. Total energy 6.6 billion electron volts, 7 times its rest mass energy, 99. 9%, 21 billion electron volts, 22 times its rest mass, 99.99%, 66 billion electron volts. Do you see the pattern? Each step requires vastly more energy than the one before, and the closer you get to C, the worse it becomes. At CERN's Large Hadron Collider, protons are accelerated to 99.9999991%, the speed of light. At this speed, each proton has about 7,000 times its rest mass energy, the final zero. 9%, the gap between where the protons are and where light is, contains more energy than all the acceleration before it. In fact, it contains infinite energy. You could pour all the energy in the universe into a single proton, and you still couldn't push it that last infinitesimal distance to C. This is the wall, not made of matter, made of geometry. The equation that describes this is elegant and unforgiving. E equals gamma, mc squared, where gamma is the Lorentz factor. Gamma equals 1 over the square root of 1 minus v squared over c squared. As velocity v approaches c, the denominator approaches 0 and gamma approaches infinity. Energy required infinite. But why? Why does the universe behave this way? Why does acceleration become harder the faster you go? The answer lies in the nature of space-time itself. Remember, you're not just moving through space. You're moving through space-time, and your total velocity through space-time is always c. When you're at rest in space, all your motion is through time. As you accelerate through space, you trade time motion for space motion, but the total remains constant. This means that as you approach the speed of light through space, you're approaching zero velocity through time. You're asymptotically reaching the boundary where time stops. And because your motion through space-time is fixed at c, pushing closer to that boundary requires exponentially more energy. Think of it like climbing an infinitely steep hill. The first steps are easy, but each step gets steeper and steeper until the slope becomes vertical, then beyond, vertical approaching the impossible. You can't reach the top, not because you're weak, but because the top doesn't exist within the geometry you're climbing. Now, let's talk about something that confuses many people: relativistic mass. Some books say that objects gain mass as they move faster, that an electron moving at 99% c is heavier than an electron at rest. Other books say this is misleading, that mass is invariant and only energy increases. Both are correct in a sense. The confusion arises from terminology. In modern physics, when we say mass, we usually mean rest mass, also called invariant mass, the mass an object has in its own reference frame. This doesn't change. An electron is always an electron, with a rest mass of about 9.11 times 10 to the power of minus 31 kilograms, no matter how fast it's moving. But the energy of that electron does increase with velocity, and energy has inertia. So, from the perspective of someone watching the electron zoom past, it behaves as if it's heavier. It's harder to deflect, harder to accelerate, further, harder to stop. This effective increase in inertia is what older textbooks called relativistic mass. The key insight is this: whether you call it increased mass or increased energy, the result is the same. The faster something moves, the more resistant it becomes to further acceleration. And at the speed of light, the resistance becomes absolute. Let's consider a practical example. The fastest spacecraft humans have ever built is the Parker Solar Probe, which reached a speed of about 163 kilometers per second, or 0.05%, the speed of light during its close approaches to the Sun. At this speed, relativistic effects are negligible. The probe's energy is only about 0.00001% greater than its rest mass energy. But imagine we wanted to accelerate the Parker Solar Probe to 10% the speed of light. We'd need to increase its kinetic energy by about 0.5% of its rest mass energy. That's enormous. The probe has a mass of about 700 kilograms. 0.5% of its rest mass energy using E equals mc squared is about 3 times 10 to the 14th power joules. That's roughly the energy output of a large nuclear power plant running for an entire day. Now imagine 90% the speed of light. You'd need to add energy equivalent to 130% of the probe's rest mass. That's more energy than you'd get from completely converting 900 kilograms of matter into pure energy. And 99.9%. You'd need 21 times the rest mass energy, the equivalent of annihilating 14,000 kilograms of matter. These aren't engineering challenges, they're fundamental limits. The energy requirements scale faster than any conceivable propulsion system could provide. But here's something many people miss from the perspective of the traveler: things look different. Suppose you're on a spaceship accelerating constantly at 1 gravity 9.8 meters per second, squared the same acceleration you feel standing on Earth. To you inside the ship, you feel a constant, comfortable push. You're not pushing against any wall. You're not feeling any resistance. But from Earth's perspective, your velocity approaches c asymptotically. After 1 year of constant acceleration, you're moving at about 77% the speed of light. After 2 years, 97%. After 10 years, 99.9999%. But you never reach C. You get closer and closer, but the gap never closes. Meanwhile, from your perspective, something else happens. The universe ahead of you appears compressed, distances shrink due to length contraction, and time on Earth appears to slow down. You can travel enormous distances in what feels like a short time. If you accelerated at 1 gravity for 12 years by your clock, you could travel about 2 million light years and reach the Andromeda Galaxy. But when you arrived, 2 million years would have passed on Earth. This is the trade-off. You can cover vast distances in your lifetime, but you can never outrun causality, never break the speed limit, never cross the boundary where time stops. Some people wonder, what if we used antimatter? When matter and antimatter collide, they annihilate, completely converting 100% of their mass into energy. That's the most efficient energy source possible. Could we use antimatter rockets to reach the speed of light? No. Even with perfect efficiency, even if you could convert all your fuel into kinetic energy with no losses, you'd still hit the same wall. The mathematics doesn't care where the energy comes from. As you approach D, the energy required grows without bound. You'd need an infinite amount of fuel to reach C, and an infinite amount of time to burn it. There's a subtle point here worth pausing on. The speed limit isn't about the strength of your engine or the efficiency of your fuel. It's about the structure of space-time. Every joule of energy you add doesn't just push you faster through space. It changes your relationship with time. It increases your inertia in a way that makes the next joule less effective. The universe absorbs the energy, redistributes it, keeps you bound to the causal structure. Think of it like running through water. The faster you try to move, the more the water resists. But in space-time, the resistance isn't friction, it's geometry. The faster you move through space, the more your motion through time slows, and the more energy it takes to shift that balance further. This has been tested countless times. Every particle accelerator on Earth confirms it. When physicists accelerate electrons in a synchrotron, they measure the energy input and the velocity output. The relationship matches the relativistic equations perfectly. The electrons behave exactly as if they're gaining inertia, becoming harder to accelerate approaching, but never reaching C. In 1964, William Bertozzi conducted a famous experiment at MIT. He accelerated electrons to various speeds and measured their kinetic energy. At low speeds, the classical equation Ke equals 1/2 MeV squared worked fine. But as speeds increased, the electron's kinetic energy grew much faster than the classical equation predicted. At 0.5 C, they had 15% more energy than expected. At 0.8 C, 3 times more. At 0.99 C, 10 times more. The data matched Einstein's equations exactly. The speed limit holds. Not as a barrier you hit, but as an asymptote, you approach a horizon you can never cross no matter how much energy you expend. And this brings us to a profound realization. The speed of light isn't really about speed at all. It's about the exchange rate between energy and inertia, between motion through space and motion through time, between the kinetic and the causal. Mass is the anchor that keeps us bound to time. The more mass you have, the more energy it takes to move you. And the faster you move, the more your energy contributes to your inertia, creating a feedback loop that spirals toward infinity as you approach C. Light escapes this loop because it has no rest mass. 0. And 0 times, anything is 0. So light carries energy, but that energy doesn't create inertia, doesn't slow it down, doesn't bind it to time. Light is pure motion, unanchored eternal, moving at the only speed it can possibly move. We, on the other hand, are anchored, not by chains but by mass. And mass is not a burden, it's what gives us time. It's what allows us to experience duration, to have pasts and futures, to change and grow and remember. The price of time is the speed limit, and maybe that's not a price at all, maybe it's a gift. But the universe has more to show us, because mass doesn't just create inertia, it also bends space-time itself. And that bending creates another kind of limit, another boundary, another way the cosmos protects its structure. There's a thought experiment Einstein loved. Imagine you're in an elevator floating in deep space far from any star or planet. There's no gravity. You and everything around you drift weightlessly. Now, imagine someone starts pulling the elevator upward, accelerating it at exactly 9.8 meters per second, squared the same rate you'd fall toward Earth. Suddenly, you're pressed against the floor. Objects fall when you drop them. Everything feels exactly like it does on Earth. And here's the question Einstein asked. Is there any experiment you could do, any measurement you could make inside that elevator that would tell you whether you're being accelerated through space or sitting still in a gravitational field? The answer he realized is no. Acceleration and gravity are indistinguishable. They're two ways of describing the same thing. This simple insight opened the door to general relativity, Einstein's theory of gravity. And embedded within it is another reason why the speed limit exists not just as a property of motion, but as a feature of space-time's geometry itself. Let's step back for a moment. In Newton's view, gravity was a force. Massive objects attracted each other through empty space, pulling on each other instantaneously, no matter how far apart they were. It worked beautifully for centuries, predicting planetary orbits, explaining tides, guiding spacecraft to the moon. But Einstein saw something deeper. Gravity isn't a force pulling objects together. It's the curvature of space-time itself. Mass doesn't pull on other mass. Mass bends the fabric of space-time, and objects follow the curves. Imagine space-time as a stretched rubber sheet. Place a bowling ball in the center. The sheet curves, creating a valley. Now, roll a marble nearby. It doesn't fall straight toward the bowling ball. It follows the curve of the sheet, spiraling around the valley. That's not a force pulling the marble. That's geometry guiding its path. This is what planets do. Earth doesn't orbit the sun because the sun pulls it. Earth moves in a straight line through space-time, the straightest path possible, given the curvature the sun creates. We call this path a geodesic. And what looks like circular motion through space is actually straight motion through curved space-time. In 1915, Einstein wrote down the equation that describes this curvature: G mu nu equals 8 pi g over c, to the fourth power, T mu nu. On the left side, G mu nu represents the curvature of spacetime, how much it bends. On the right side, T mu nu represents the distribution of mass and energy. The equation says mass and energy tell spacetime how to curve, and spacetime tells mass and energy how to move. Notice something about that equation. The speed of light c appears in it. Not because light is special, but because c is the conversion factor between space and time, between energy and curvature. It's woven into the geometry. And that means the speed limit isn't imposed on spacetime, it's part of spacetime's structure. Let's explore what this means. When spacetime curves, it doesn't just bend space, it bends time. Near a massive object, time runs slower. Clocks tick at different rates depending on how deep they are in the gravitational field. This is called gravitational time dilation, and it's been measured precisely. In 1976, NASA launched an experiment called Gravity Probe A. A rocket carried an atomic clock to an altitude of 10,000 kilometers, then let it fall back to Earth. During the flight, scientists compared the clock's ticking rate to an identical clock on the ground. The elevated clock farther from Earth's mass ran faster by exactly the amount Einstein's equations predicted, about 4.3 parts in 10 billion. 4 billionths of a second faster per second. Tiny, but measurable. Real. This effect has practical consequences. GPS satellites orbit at about 20,000 kilometers altitude where Earth's gravity is weaker. Time there runs faster than on the ground by about 45 microseconds per day. The satellites are also moving, which causes time dilation in the opposite direction, slowing their clocks by about 7 microseconds per day. The net effect: GPS satellite clocks run about 38 microseconds fast each day. If engineers didn't correct for this, GPS coordinates would drift by about 10 kilometers per day. Your navigation would be useless. The system works only because it accounts for the curvature of space-time. Now, here's where the speed limit comes in. The curvature of space-time affects not just how objects move, but how fast they can move. In curved space-time, the geometry itself enforces the limit. Think of it this way. When space-time curves, it changes the relationship between distance and time. A path through curved space-time is longer in a sense than the same path through flat space-time. And because the speed limit is geometric, built into the metric of space-time itself, it applies no matter how warped or twisted the fabric becomes. This was tested in 1964 by Erwin Shapiro, who measured how long it took radio signals to travel from Earth to Venus and back when the signals passed close to the Sun. The signals took slightly longer than expected, about 200 microseconds longer. Not because they slowed down, but because the Sun's mass curved the path they followed and stretched the space-time they traveled through. This is called the Shapiro delay, and it's been measured countless times since, always confirming Einstein's predictions. Light always travels at c locally, but the path it takes through curved spacetime can be longer than it appears. But there's a limit to how much spacetime can curve. Push it too far, and something extraordinary happens. The curvature becomes so extreme that not even light can escape. You create a black hole. Every mass has what's called a Schwarzschild radius, named after Carl Schwarzschild, who found the first exact solution to Einstein's equations in 1916, just months after Einstein published general relativity. Schwarzschild was a German astrophysicist serving in the German army during World War I. While stationed on the Russian front in between artillery calculations, he solved Einstein's equations for the spacetime around a spherical mass. The Schwarzschild radius is the radius at which, if you compressed an object's mass into a sphere, that small space-time curvature would become so intense that the escape velocity would equal the speed of light. For Earth, the Schwarzschild radius is about 9 millimeters. If you could compress the entire mass of Earth, 6 trillion kilograms, into a sphere smaller than a marble, it would become a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. Compress the sun's mass into a ball the size of a small town, and space-time curves so sharply that light cannot escape. For a typical human, it's about 10 to the power of minus 25 meters, far smaller than an atomic nucleus, smaller than anything we can measure. These numbers seem absurd, but they reveal something profound. The speed limit determines not just how fast things can move, but how much space-time can curve before it reaches a point of no return. At the Schwarzschild radius, something called the event horizon forms. This is a boundary in space-time, a surface of no return. Not a physical barrier. There's no wall, no membrane, no substance, just geometry. A point where the curvature becomes so steep that all future paths point inward. Cross that boundary, and every direction you can move leads deeper into the black hole. You can't turn around. You can't stop. You can't escape. Not because something is pulling you, but because the geometry of space-time itself gives you no outward path. The curvature is so extreme that even moving at the speed of light in what you think is an outward direction still results in falling inward. Light emitted exactly at the event horizon orbits there trapped on the boundary, unable to climb out of the gravitational well or fall in. Light emitted just inside falls inward, following space-time's curve toward the center. And this is tied directly to the speed limit. The event horizon exists precisely at the distance where escape velocity equals c. Anything trying to escape from inside would need to move faster than light. And because nothing can do that, because c is the geometric limit written into space-time structure, nothing escapes. It's not a coincidence. The speed limit and the curvature limit are two expressions of the same underlying structure. Space-time can only bend so much before it creates a boundary that even light cannot cross. Let's make this more concrete. Imagine you're watching someone fall toward a black hole from a safe distance. As they approach the event horizon, something strange happens from your perspective. They appear to slow down. Their movements become sluggish, as if they're moving through thick syrup. The light coming from them becomes redshifted dimmer, stretched to longer wavelengths. From your perspective, far from the black hole where space-time is relatively flat, they never quite reach the horizon. They freeze there, asymptotically approaching the boundary, but never crossing it. Their image fading as the light becomes too redshifted to see stretched to infrared, then radio waves, then wavelengths so long you can't detect them anymore. But from their perspective, from the perspective of the person falling, they cross the horizon in finite time. They don't feel anything special at the moment of crossing. There's no jolt, no barrier, no sensation. The horizon isn't a physical surface. It's just a point in space-time where the geometry changes, where the relationship between past and future shifts fundamentally. Once across, they fall inexorably toward the center, toward the singularity where space-time curvature becomes infinite and all our equations break down. This asymmetry, the difference between what you see and what they experience, is another consequence of the speed limit. Information can't travel faster than light, so the light carrying information about them crossing the horizon is stretched and delayed infinitely. You never receive it. The speed limit prevents you from witnessing what happens beyond the event horizon. There's something almost protective about this. The speed limit shields you from seeing the ultimate fate of anything that falls into a black hole. You see it approach the edge, watch it fade to darkness, and that's all. What happens inside remains forever, beyond your causal reach. Physicists call this the cosmic censorship hypothesis proposed by Roger Penrose in 1969. It suggests that the universe hides its singularities behind event horizons, preventing naked singularities, points of infinite curvature visible to the outside universe, from existing. If naked singularities did exist, they'd break the predictability of physics, create paradoxes, allow information to emerge from regions where causality breaks down. The speed limit enforces this censorship. It ensures that regions of extreme space-time curvature remain isolated, cut off, unable to influence the rest of the universe in ways that would violate causality. But here's something most people don't realize. You don't need a black hole to see the connection between gravity and the speed limit. Every massive object creates a gravitational field, and that field is really just curved spacetime. And curved spacetime affects the paths that light and matter take through it. Think about Earth. When you stand on the surface, you're at the bottom of a gravitational well. Spacetime is curved around you. Time runs slightly slower for you than it does for someone in orbit or far out in space. This isn't noticeable in daily life. The difference is measured in microseconds per day, but it's real, measurable, and built into the technology we use. When a GPS satellite sends a signal to your phone, that signal travels through slightly curved space-time. The curvature affects the signal's path and the time it takes to arrive. The satellite's onboard computer accounts for this adjusting, for both the time dilation caused by the satellite's velocity and the gravitational time dilation from being farther from Earth's center. Without these corrections, without accounting for curved space-time, GPS would accumulate errors of about 10 kilometers per day. The system only works because engineers understand that space-time is curved, that time flows at different rates in different places, and that these differences are governed by the same constant that limits the speed of light. The speed of light isn't just a speed, it's a fundamental ratio written into space-time's geometry. It tells you how space and time relate to each other, how curvature translates into acceleration, how mass bends the paths that everything, including light itself, must follow. And because c is finite, because there's a maximum speed at which information can propagate, space-time can only curve so far before it creates boundaries, event horizons, points of no return, edges of causality. Remove the speed limit and these boundaries disappear. Black holes couldn't exist, at least not in the same way. Singularities would be naked, visible, unprotected. The causal structure of space-time would unravel. So, in a strange way, the speed limit is what allows gravity to create black holes. It's what makes event horizons possible. It's what ensures that the most extreme curvatures remain hidden, isolated, unable to corrupt the causal fabric of the rest of the universe. Gravity and the speed limit aren't separate phenomena. They're woven together in Einstein's equations, two aspects of the same geometric structure. Mass curves space-time. Curvature affects how fast things move, and that maximum speed is set by c, the constant that unifies space-time mass, energy, and causality into one coherent whole. When you drop an object and watch it fall, you're watching it follow a geodesic through curved space-time. When you see light bend around the sun during an eclipse, a phenomenon first observed by Arthur Eddington in 1919, confirming Einstein's theory, you're seeing light follow the straightest possible path through space-time that's been curved by the sun's mass. And when you realize you can never outrun light, never exceed c, never escape the causal structure of reality, you're confronting the geometric limit that holds everything together. The universe has a speed limit because space-time has a geometry, and that geometry has rules, and those rules prevent paradoxes, protect causality, and keep the story of existence coherent from beginning to end. But push that geometry to its extreme, compress enough mass into a small enough space, and something breaks. Or rather, something changes so fundamentally that we can barely comprehend it. Imagine standing at the edge of a waterfall, not a gentle cascade, but a massive roaring fall where water plunges into darkness. You're in a boat paddling upstream, fighting the current. Near the shore, it's easy. The water moves slowly. You make progress. But as you paddle closer to the edge, the current strengthens. You paddle harder, but you're barely holding position. A little closer, and no amount of paddling helps. The current is too strong. You're pulled toward the edge faster and faster until you go over. Now, replace the water with space-time. Replace the edge with an event horizon, and replace your paddle with light itself. That's a black hole. We've talked about how space-time curves, how mass bends the fabric of reality, how the speed limit emerges from geometry. But there's a point where curvature becomes so extreme that space-time doesn't just bend, it breaks. Or rather, it transforms into something so alien that our normal concepts of space-time and causality stop working. That point is called a singularity, and it's hidden inside every black hole, veiled behind an event horizon, protected by the speed limit itself, from revealing its full strangeness to the outside universe. Let's start with what we know. In 1916, just months after Einstein published his theory of general relativity, Carl Schwarzschild found a solution to Einstein's equations that described the space-time around a perfectly spherical, non-rotating mass. He was serving in the German army during World War I, stationed on the Eastern Front, and he worked on these equations between artillery calculations, scribbling in notebooks by candlelight. What Schwarzschild discovered was remarkable. His solution showed that for any mass there exists a critical radius, now called the Schwarzschild radius, where something dramatic happens. At this radius, the escape velocity equals the speed of light. For the Sun, that radius is about 3 kilometers. For Earth, about 9 millimeters. For a human body, smaller than a proton. These numbers are so small compared to the actual sizes of these objects that they seem meaningless. The Sun is 700,000 kilometers in radius. How could 3 kilometers matter? But if you could compress the Sun, squeeze all its mass into a sphere just 6 kilometers across, then the Schwarzschild radius would lie outside the surface. And at that boundary, something profound happens. Space-time curves so sharply that not even light moving straight up can escape. The geometry becomes a trap. This boundary is the event horizon, not a physical surface, not a membrane or a wall, just a point in space-time where the geometry changes so drastically that all future paths lead inward. Cross it, and you cannot come back. Not because something pulls you, but because back, in the sense of moving away from the center, ceases to exist as a possible direction in space-time. Think about what this means. Inside the event horizon, the future direction in space-time points toward the singularity, not might point or usually points. Must point. It's as inevitable as time moving forward outside the black hole. Once you're inside, reaching the singularity isn't something you can choose to avoid. It's something that will happen, is happening in your future, as certain as the next moment of time. For decades after Schwarzschild's solution, physicists debated whether black holes could actually exist or were just mathematical curiosities. Einstein himself didn't believe they were real. In 1939, he published a paper arguing that physical processes would prevent their formation. But in 1939, Robert Oppenheimer and his student Hartland Snyder showed that when a massive star exhausts its nuclear fuel, nothing can stop its collapse. If the core is heavy enough more than about 3 times the mass of the Sun, no known force can counteract gravity. The core collapses, density rises without limit, and a black hole forms. The evidence came slowly. In 1964, the first black hole candidate was discovered Cygnus X-1, an invisible object in orbit with a blue supergiant star pulling matter from the star and heating it to millions of degrees, causing it to emit X-rays. The invisible companion was too massive to be a neutron star. It had to be something else. By the 1970s, the consensus shifted. Black holes weren't just possible, they were inevitable. Massive stars die. Some explode as supernovae, leaving behind neutron stars. Others collapse entirely, leaving only warped space-time behind. Today we know there are millions of stellar-mass black holes in our galaxy alone. And at the center of nearly every large galaxy, including our own, seats a supermassive black hole millions or billions of times the mass of the Sun. The one at the center of the Milky Way called Sagittarius. A star has a mass of about 4 million solar masses compressed into a region smaller than Mercury's orbit. In 2019, the Event Horizon Telescope, a network of radio telescopes spanning the globe, captured the first direct image of a black hole's shadow, the region around the event horizon where light cannot escape. The black hole at the center of the galaxy, M87, has a mass of 6.5 billion solar masses. The image showed exactly what Einstein's equations predicted, a dark circle surrounded by a glowing ring of superheated matter spiraling inward. The black hole itself, the event horizon, emits no light. it's invisible. We see only the light from matter just outside matter that's still free to escape, still able to send photons outward to our telescopes. But what happens to the matter that crosses the horizon? What happens to the light, the information, the structure of everything that falls in? This is where our understanding begins to fracture. Inside the event horizon, space-time is so warped that the radial direction, the direction toward the center, becomes time-like. Moving toward the singularity isn't a choice you make by moving through space. It's something that happens as time passes. Just as you can't stop time from moving forward outside a black hole, you can't stop yourself from reaching the singularity once you're inside. And the singularity itself, it's a point where space-time curvature becomes infinite, where density becomes infinite, where the equations of general relativity produce infinities and stop making sense. Physicists don't believe the singularity is literally a point of infinite density. More likely, it's a sign that general relativity breaks down, that we need a deeper theory, a theory of quantum gravity to describe what really happens at the center of a black hole. But we don't have that theory yet. Not completely. And so, the singularity remains a mystery hidden behind the event horizon, protected by the speed limit from revealing its secrets to the outside universe. There's a principle Roger Penrose proposed in 1969 called the cosmic censorship hypothesis. It states essentially that singularities are always hidden inside event horizons. Nature, it seems, refuses to allow naked singularities, points of infinite curvature, visible to the rest of space-time, to exist. Why? Because naked singularities would break the predictability of physics. Near a singularity, space-time curvature becomes so extreme that we can't predict what might emerge from it. Particles' radiation information could appear without cause, violating causality, creating paradoxes. The event horizon prevents this. It acts as a one-way membrane. Things can fall in, but nothing comes out, at least not in the classical picture. The singularity's influence is confined. The rest of the universe remains safe, predictable, causal. But in 1974, Stephen Hawking discovered something astonishing. Black holes aren't entirely black. They emit radiation. The mechanism is subtle. Near the event horizon, quantum fluctuations in the vacuum create pairs of virtual particles, a particle and its antiparticle, that normally annihilate each other almost instantly. But near the horizon, sometimes one particle falls in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. This is called Hawking radiation, and it means black holes slowly evaporate. They lose mass over time. A stellar mass black hole would take longer than the current age of the universe to evaporate completely. But in principle, given enough time, every black hole will eventually disappear. This creates a profound puzzle. When matter falls into a black hole, it carries information. The arrangement of particles, the quantum states, everything that defines its structure. If the black hole evaporates, emitting only thermal radiation with no structure, where does that information go? This is the black hole information paradox, and it's one of the deepest problems in theoretical physics. Does information get destroyed, violating the principles of quantum mechanics? Does it escape somehow encoded in the Hawking radiation in ways we don't yet understand? Or does it remain inside, trapped even as the black hole shrinks to nothing? We don't know. The answer requires a complete theory of quantum gravity, something we're still working toward. But here's what we do know. The event horizon exists because of the speed limit. It's the boundary where escape velocity equals c. And because nothing can exceed c, nothing inside can escape, at least not through ordinary means. If you could move faster than light, event horizons wouldn't trap you. You could dive into a black hole and come back out. You could see the singularity probe, its nature, extract information from inside. But you can't. The speed limit prevents it. In this way, the speed limit protects the universe from the full strangeness of singularities. It keeps them hidden, isolates them, ensures that their breakdown of physics remains local, unable to corrupt the causal structure of space-time beyond the horizon. Some people imagine black holes as cosmic vacuum cleaners, sucking in everything nearby. That's a misconception. From a safe distance, a black hole's gravity is no different from any other object of the same mass. If the sun became a black hole right now, same mass, just compressed Earth's orbit wouldn't change. We'd still orbit at the same distance at the same speed. We'd freeze in the darkness, but we wouldn't fall in. Black holes only become inescapable when you cross the event horizon. And the size of that horizon depends entirely on the mass. For a stellar mass black hole, the horizon is only a few kilometers across. For a supermassive black hole, it can be millions of kilometers. But in both cases, the principle is the same. Inside spacetime is so warped that escape requires faster-than-light travel. Now, let's talk about something even stranger: the way time behaves near a black hole. If you're watching someone fall toward an event horizon, you see their time slow down. The closer they get, the slower they move. Light from them becomes increasingly redshifted. Their clock appears to tick slower and slower. At the horizon, time from your perspective stops. You never see them cross. You watch them asymptotically approach the boundary, their image freezing, fading, redshifted into invisibility. As far as you're concerned, they're frozen at the horizon forever. But from their perspective, time continues normally. They fall freely across the horizon in finite time and continue toward the singularity. They don't feel anything special at the horizon. There's no surface, no barrier. Just empty space warped in a way that changes the meaning of forward and backward. This difference, the asymmetry between what you see and what they experience, comes directly from the way space-time curves. The speed limit ensures that light from inside the horizon never reaches you, so you never receive information about them crossing. You're causally disconnected from everything beyond the horizon. In a sense, the event horizon is less a place and more a moment. It's the moment when someone's future becomes disconnected from yours. After they cross, no signal, they send no light they emit can ever reach you. They can still see you, still receive light from outside, but they cannot send anything back. Inside, strange things happen. Space-time is so curved that the singularity lies not in a direction through space, but in a direction through time. It's not somewhere you can travel to by moving. It's someone, a moment in your future that you will inevitably reach as time passes. How long does it take to reach the singularity once you've crossed the horizon? For a solar mass black hole, about 10 microseconds. For Sagittarius, a star, the supermassive black hole at our galaxy's center, about 30 seconds. You would have half a minute to look around to witness whatever exists in that incomprehensible space, before space-time curvature becomes infinite and you're torn apart by tidal forces stretched into a stream of particles in a process physicists whimsically call spaghettification. But even this assumes our current understanding holds. Near the singularity, quantum effects become important. Space-time itself might dissolve into something more fundamental: quantum foam, strings, loops, structures we can barely describe with current mathematics. The singularity is where our maps end, where the equations break down, where the universe says, here, at this boundary of knowledge, you must wait for a deeper theory. And the speed limit is what keeps us from seeing this breakdown. It enforces a cosmic censorship, hiding the singularity behind a one-way membrane, ensuring that its strangeness remains isolated, unable to spread outward, unable to unravel the causal fabric of the wider universe. So, when we ask why black holes exist, part of the answer is because the speed limit exists. The limit creates boundaries. It makes event horizons possible. It ensures that extreme curvature remains hidden. Without C, without the geometric constant that ties space and time together, black holes would be impossible. Or at least, they'd be very different naked singularities, visible to all, unpredictable, dangerous to the logical structure of reality. The universe is careful about this, almost obsessively protective. Every mechanism, every law seems designed to prevent causality from breaking down, to keep the past fixed and the future open, to maintain the order that makes physics possible. And at the heart of that protection is the speed limit, not a rule, not a prohibition, but a feature of geometry, a consequence of how space-time works, a boundary that keeps existence coherent. Black holes are not flaws in the universe, they're predictions, natural consequences of general relativity. And they exist precisely because space-time has a structure, and that structure has limits, and those limits are defined by c. But black holes are extreme, rare in cosmic terms. Most of space-time is nearly flat, barely curved, gentle, and predictable. And in that gentle space-time, the speed limit shows up in quieter ways, in the ticking of clocks, in the paths of satellites, in the technology we use every day without thinking about the curved geometry beneath it. Right now, there are at least 24 satellites orbiting above you, about 20,000 kilometers up, moving at roughly 14,000 kilometers per hour. Each one carries an atomic clock precise to within billionths of a second, and every one of those clocks is running faster than the clock on your phone. Not broken, not miscalibrated, faster. Because time itself flows at a different rate up there than it does down here. This isn't theory. It's not abstract mathematics scribbled on a blackboard. It's reality measured and corrected every moment of every day, woven into the technology that tells you where you are, how to get where you're going, and when you'll arrive. Without accounting for the speed limit and the curvature of space-time, GPS wouldn't work. Your location would drift by kilometers each day. Navigation would be impossible, and we'd have undeniable everyday proof that time is not universal, that clocks tick at different rates, depending on how they move and where they sit in the gravitational well. The universe has a clock, or rather it has many clocks all ticking at different rates, all connected by the geometry of space-time, all bound by the speed limit that determines how fast information can travel between them. Let's start with something simple. Two identical atomic clocks, the most precise timekeeping devices ever made. One stays on the ground, the other goes on a journey. In October 1971, Joseph Haffel and Richard Keating, two physicists, boarded commercial airline flights carrying 4 cesium beam atomic clocks. They flew around the world twice, once eastward with Earth's rotation and once westward against it. When they returned and compared the traveling clocks to identical clocks that had remained at the United States Naval Observatory, they found differences. The eastward clocks, which had been moving faster relative to Earth's center due to the planet's rotation, had lost 59 nanoseconds. The westward clocks, moving slower relative to Earth's center, had gained 273 nanoseconds. 59 billionths of a second. 273 billionths. Tiny amounts, but predicted precisely by Einstein's equations. Special relativity said the moving clocks should run slower. General relativity said the higher altitude clocks should run faster due to weaker gravity. Combine both effects and you get the exact numbers they measured. Time is not absolute. It flows at different rates for different observers, depending on their velocity and their position in a gravitational field. This is time dilation, and it's been tested thousands of times since then in laboratories and particle accelerators in space and in the technology we carry in our pockets. GPS satellites orbit Earth at about 20,200 kilometers altitude, where gravity is weaker than on the surface. According to general relativity, time should run faster there, about 45 microseconds per day, faster than clocks on the ground. But the satellites are also moving at about 14,000 kilometers per hour relative to Earth's surface. According to special relativity, this motion causes time to run slower, about 7 microseconds per day slower. The net effect, GPS satellite clocks run about 38 microseconds fast each day compared to clocks on Earth. 38 millionths of a second doesn't sound like much, but light travels at 299,792 kilometers per second. In 38 microseconds, light travels about 11 kilometers. If GPS didn't correct for time dilation, your position would drift by more than 10 kilometers each day. Within a week, the system would be useless. So, GPS satellites don't just measure time. They measure time as it flows in their reference frame, then adjust for the fact that time flows differently on Earth's surface. Every navigation calculation you make, every turn-by-turn direction, every you have arrived at your destination, depends on accounting for the curvature of spacetime and the speed limit that governs how signals travel through it. Think about that. You're holding technology that works only because engineers understand that time is relative, that gravity bends space-time, that clocks tick at different rates depending on where they are and how fast they're moving. This is not exotic physics happening in the distant galaxies. It's happening here now, in orbit above you, and it proves every day that the speed limit is real, that space-time is curved, that Einstein was right. But GPS is just one example. Let's go deeper. In 1976, NASA launched Gravity Probe A rocket carrying a hydrogen-Moser atomic clock. The rocket climbed to an altitude of about 10,000 kilometers, then fell back to Earth. During the flight, scientists compared the rocket's clock to an identical clock on the ground using radio signals. The result: the elevated clock farther from Earth's mass ran faster. Over the course of the 2-hour flight, it gained about 4.3 parts in 10 billion, about 0.00000000043 seconds per second, faster than the ground clock. This confirmed gravitational time dilation with exquisite precision. Time doesn't just flow. It flows at rates determined by the curvature of space-time, by how deep you are in a gravitational well, by how close you are to mass. Now, here's something subtle. People often think time dilation is about clocks being affected by motion or gravity, but it's not the clocks that change. It's time itself. The clocks are just measuring the passage of time in their local space-time, and that passage genuinely differs from place to place. Imagine two twins. One stays on Earth. The other boards a spaceship and travels at 90% the speed of light to a distant star and back. When they reunite, the traveling twin has aged less, not because their body was affected by speed, but because they experienced less time. Fewer moments passed for them. Their heart beat fewer times. They took fewer breaths. Less time elapsed. This is the twin paradox, though. It's not really a paradox. It's a prediction of special relativity, and it's been confirmed using particles called muons. Muons are unstable particles created when cosmic rays, high-energy particles from space, collide with atoms in Earth's upper atmosphere. A muon at rest lives for about 2.2 microseconds before decaying into other particles. That's its half-life. The upper atmosphere where muons are created is about 10 kilometers above sea level. If a muon travels at the speed of light, it would take about 33 microseconds to reach the ground. But the muon only lives for 2.2 microseconds. It should decay long before reaching the surface. Yet, muons reach the ground constantly. Detectors at sea level measure them all the time. How the muons are traveling at about 98% the speed of light. From our perspective, their internal clocks run slow. Time dilation stretches their 2 microseconds to about 15 microseconds in our reference frame, plenty of time to reach the ground. From the muon's perspective, something else is happening. It experiences only 2.2 microseconds, but the distance to the ground is contracted. Length contraction. Another prediction of special relativity compresses the 10 kilometers to about 1.4 kilometers from the muon's point of view. So, it covers a shorter distance in its brief lifetime and reaches the ground just fine. Two perspectives, both correct, both describing the same event using the geometry of space-time. This was first observed in 1941 by Bruno Rossi and David Hall, who placed particle detectors at different altitudes on Mount Washington in New Hampshire. They counted muons at the summit and at the base. The numbers match the predictions of time dilation perfectly. Since then, countless experiments have confirmed this. Particles in accelerators, atomic clocks on airplanes, satellites in orbit. Every test shows the same thing: time is not a universal constant. It's a local phenomenon shaped by motion and gravity governed by the geometry of space-time. But here's where it gets personal. You experience time dilation every day even if you don't notice it. When you're sitting still, you're not moving through space, but you are moving through time at the maximum rate possible for your reference frame. When you start walking, some of your motion through time converts to motion through space. You move through time slightly slower, by an amount so small you'd need atomic clocks to measure it, but it's real. When you drive in a car at highway speeds, you age microscopically slower than someone standing still. When astronauts spend months on the International Space Station, orbiting at 28,000 kilometers per hour, they age about 0.01 seconds less than they would have on the ground. Tiny amounts, but they add up, and they prove something profound. Your experience of time depends on your path through space-time. Think about what this means. There's no single now that extends across the universe. When you look at a star 100 light years away, you're seeing light that left 100 years ago. But someone moving very fast relative to you might see light from a different moment in that star's history. What's simultaneous for you isn't simultaneous for them. Simultaneity is relative. The present moment is not a universal slice through space-time. It's a perspective dependent on your motion, on your position, on your path. This is why the speed limit matters. It's what keeps different reference frames connected. Light travels at sea in all frames, providing a common thread, a way to compare clocks, to synchronize events, to maintain causality, even when time flows at different rates. Without the speed limit, there'd be no way to relate one clock to another, no way to say what happened first, no causal structure, just chaos. Now let's talk about something most people misunderstand. Time dilation near Earth is small, barely noticeable, but near a black hole, it becomes extreme. Imagine you're watching someone approach a black hole. As they get closer to the event horizon, you see them slow down. Their movements become sluggish. Light from them becomes increasingly redshifted, stretched to longer wavelengths, dimmer. At the horizon, from your perspective, they freeze. Time for them, as you observe it, stops. You never see them cross. They appear to hover at the boundary forever, their image fading into darkness. But from their perspective, time continues normally. They fall freely across the horizon in finite time and continue toward the singularity. They don't feel time slowing. They don't feel anything special. This difference is gravitational time dilation, taken to the extreme. Near the event horizon, space-time is so curved that time as measured far away runs infinitely slow. But locally, time flows at its normal rate. This creates something strange. If you could hover just above the event horizon of a supermassive black hole, close enough that time for you ran at half the rate of someone far away, and you stayed there for what felt like 1 year, then returned 2 years, would have passed for the outside universe. You could in principle use this as a time machine, not to travel to the past, but to skip forward into the future. Sit near a black hole, wait, then leave. You've aged 1 year, but the universe has aged 2 or 10 or 1,000, depending on how close you got and how long you stayed. This is called gravitational time dilation, and it's perfectly consistent with general relativity. Time flows at different rates in different gravitational fields. The deeper the well, the slower the clock. There's a beautiful symmetry here. Motion through space slows time. Gravity slows time. Both are aspects of the same geometry. Both are consequences of space-time curvature. And both are limited by c, the speed at which causality propagates. Now, let's come back to something practical. The fact that GPS works proves that space-time is curved, that time is relative, that the speed limit is real. But it also proves something more subtle: the universe is comprehensible. The equations Einstein wrote down in 1915 describe reality with astonishing precision. Engineers designing GPS didn't need to guess or approximate. They used Einstein's equations, calculated the corrections, and implemented them in software. And it works every day for billions of people across the entire planet. This is one of the great triumphs of physics, a theory developed to understand the cosmos, to explain the orbit of Mercury and the bending of starlight, turns out to govern the technology we use to navigate city streets. The universe doesn't care about our convenience. It doesn't adjust its rules to make our lives easier, but the rules are consistent. They apply everywhere from the surface of a black hole to the parking lot, where you're trying to find your car. And because they're consistent, because they're based on geometry rather than arbitrary forces, we can use them to build things that work. GPS is a testament to the reality of space-time. Every time you check your location, you're interacting with a system that accounts for time flowing at different rates, for signals traveling at the speed of light, for the curvature of the planet and the geometry of orbits, and all of it. Every correction, every adjustment, every microsecond of difference stems from the speed limit. From c, the constant that ties space and time together, that determines how fast clocks can tick relative to each other, that ensures causality holds even when time flows at different rates. The universe has a clock. Or rather, it has a rhythm, a pulse, a rate at which change propagates through space-time. And that rate is set by c. Everything else, GPS, satellites, muons, atomic clocks on airplanes, the aging of twins on different journeys follows from that. Time is not what we thought it was. It's not a river flowing uniformly, carrying everything along at the same pace. It's more like a landscape with hills and valleys, places where it flows fast and places where it slows. And we move through that landscape, each of us experiencing time at our own rate, connected to each other by light, by signals, traveling at easy by the geometry that holds it all together. So, when you use GPS, when you find your way home, when you rely on satellites orbiting overhead to tell you where you are, remember, you're navigating not just through space, but through space-time. You're depending on the fact that time is relative, that clocks tick at different rates, and that the universe has a speed limit that makes it all coherent. And that speed limit, that fundamental constant woven into the fabric of reality, is not a barrier. It's a promise. A guarantee that the past stays fixed, the future remains open, and time, though relative, still flows in a way we can measure, understand, and use. But there's one more question, one final piece of the puzzle. We've seen what the speed limit does, how it protects causality, how it shapes space-time, how it governs motion and time and gravity. But we haven't asked the deepest question of all, what does it mean? What does it mean that the universe has a speed limit? Not what does it do or how does it work, but what does it mean? What is the universe telling us by setting this boundary, by refusing to let anything outrun light, by keeping causality locked behind a geometric wall? We've traveled far tonight. We've watched Einstein imagine running alongside light. We've seen space-time bend and curve, creating valleys that planets fall into. We've felt the weight of energy as it resists acceleration, approaching infinity as speed approaches c. We've stood at the edge of black holes where geometry becomes so extreme that even light cannot escape. We've seen time flow at different rates, clocks ticking faster in orbit, slower, on the ground, frozen at the event horizon. But beneath all of this, beneath the equations, the experiments, the technology, there's something deeper, a principle, a kind of logic woven into the fabric of existence. The speed limit isn't arbitrary. It's not a number someone chose. It's a consequence of how space and time relate to each other, how energy and mass interconvert, how cause and effect remain ordered. It's the speed at which being becomes becoming, the rate at which the possible crystallizes into the actual. Think about what would happen if there were no speed limit, if information could travel infinitely fast, if effects could happen instantly everywhere the moment a cause occurred. There would be no separation between events, no time for light to travel, no delay between action and consequence. The past and future would collapse into a single eternal now. Nothing would happen in sequence. Nothing would have a story. Nothing would change in a way that made sense. Causality would break down. You could send a signal into your own past. You could prevent your own birth. The universe would be filled with paradoxes, contradictions, Events that both happen and don't happen, timelines that loop back on themselves. The speed limit prevents this. It creates distance in time. It ensures that every event has a before and an after. It preserves the order of things, the flow from cause to effect, the structure that makes stories possible. In a sense, c is the speed of narrative, the speed at which one moment leads to the next, the speed at which history unfolds. And it's not just about causality, it's about connection. When you see a star, the light reaching your eye left that star years, centuries, millennia ago. That photon traveled through the void, through the expanding space between galaxies, across distances so vast, they defy imagination. And when it reaches you, when it strikes your retina and triggers a cascade of signals in your brain, you're connected to that star, not as it is now, but as it was when the light departed. The speed limit creates this connection. It allows information to travel from one place to another, from one moment to another, carrying the imprint of where it's been, what it's encountered, how the universe has changed along the way. Without the speed limit, there'd be no such thing as light years. No looking back in time when we look out into space. No cosmic horizon. No edge to the observable universe. No history written in the wavelengths of distant starlight. The universe would be flat, instantaneous, everything visible all at once. No depth, no perspective, no journey. But because c is finite, the universe has a structure in time as well as space. We can look out and see the past. We can trace the history of the cosmos in the light that reaches us. We can watch galaxies as they were billions of years ago, see stars being born, see the afterglow of the Big Bang, itself still traveling, still arriving, carrying information about the universe when it was only 380,000 years old. The speed limit makes this possible. It turns distance into time, proximity into history, observation into archaeology. And it does something else, something even more profound. It gives us time itself. Remember what we learned earlier? Massless particles move at c and experience no time. They exist in a timeless state, an eternal now, where departure and arrival are the same moment. But particles with mass, atoms, molecules, everything that makes up your body, your thoughts, your memories, cannot reach c. They're bound to move slower, and moving slower than c means experiencing time. Mass is what anchors us to the flow of time. And the speed limit is what separates the timeless from the temporal, the eternal from the changing being, from becoming. Light doesn't age, it doesn't change. A photon created in the Big Bang is from its own perspective still being created. It hasn't experienced a single moment since then. It's frozen in the instant of its birth, even as it crosses billions of light years of space. But you age, you change, you experience duration, you remember the past, you anticipate the future. You live in time, moving through it moment by moment, because you have mass, because you cannot reach c, because the universe has bound you to the flow of causality. Is this a limitation, or is it a gift? Without time, there's no growth, no learning, no love that deepens over years, no stories that unfold, surprise, resolve, no music, because music is change in time, notes following notes, silence and sound weaving together. The speed limit gives us time, and time gives us everything that makes existence rich, meaningful, worth experiencing. So, when we ask why the universe has a speed limit, maybe the answer is so that there can be stories, so that cause can lead to effect, so that the past can inform the future, so that we can be more than frozen moments, more than eternal nows, more than timeless points in space-time. The speed limit is what makes us mortal, what makes us temporal, what gives us the gift of change. And maybe that's why it's called SE, not for constant or celerity. Though those are the usual explanations, but for something deeper, for causality, for connection, for the coherence that holds the universe together. Some people find the speed limit frustrating. It means we can never reach distant stars in a human lifetime, at least not by conventional means. It means the observable universe has an edge beyond which we cannot see, cannot reach, cannot know. It means there are limits to how fast we can communicate, how quickly we can respond, how far we can extend our influence. But these limits aren't punishments, they're protections. They keep the universe coherent. They preserve causality. They ensure that the story of existence remains comprehensible, that physics remains predictive, that the past stays past and the future stays future. And within those limits, we've built so much. We've learned to measure time to billionths of a second. We've built satellites that account for relativity to guide us through cities. We've detected gravitational waves ripples in space-time traveling at sea, carrying information about colliding black holes billions of light years away. We've imaged the shadow of a black hole, seen the light bending around the event horizon, confirmed Einstein's vision of curved space-time. We've taken the speed limit not as a barrier, but as a foundation, a principle to build on, to work with, to understand and use. And in doing so, we've glimpsed something extraordinary: the universe is knowable. Its laws are consistent. Its geometry is elegant. Its deepest principles, the speed of light, the curvature of space-time, the flow of time, are woven together in a way that makes sense, that reveals itself to patient observation, careful measurement, and creative thinking. Einstein saw this, a young man in a Peyton office imagining himself running alongside light, asking questions that seemed impossible, following the logic wherever it led. He didn't impose his will on the universe. He listened to it. He watched how it behaved, and he discovered that space and time were not separate, that mass and energy were interchangeable, that gravity was geometry, that the speed of light was not just a speed, but a fundamental constant binding everything together. He found that the universe has a speed limit not because it's slow, but because it's structured, because it has rules, because it makes sense. And those rules give us GPS. They give us particle accelerators. They give us predictions. We can test technologies. We can build a framework for understanding everything, from the orbit of Mercury to the expansion of the cosmos. But more than that, they give us wonder, the realization that the universe is stranger, deeper, more beautiful than we imagined. That time is not absolute. That space can curve. That light is eternal. That the limit we thought was a wall is actually a window into the hidden structure of reality. So tonight, as you drift towards sleep, think about this. Every photon that touches your eye is a messenger from the timeless realm, carrying information about something that happened. A star, burning a lamp, glowing a screen, flickering, traveling at the only speed it can, connecting you to the universe at large. And you experiencing time bound by mass, unable to reach C, are not separate from that universe. You're part of it, moving through space-time at your own rate, following geodesics, shaped by gravity, aging as clocks tick, connected to everything by light, by causality, by the geometry that holds it all together. The universe has a speed limit, not to keep you trapped, not to frustrate your ambitions, but to give you time, to preserve causality, to ensure that stories have beginnings, middles, and ends, to make existence coherent, knowable, meaningful. And that speed, 299,792,458 meters per second, the speed of light, the speed of causality. The speed of being is woven into every moment you experience, every breath you take, every thought that crosses your mind. It's the rhythm of the cosmos, the pulse of existence, the rate at which now becomes then and then becomes memory. And it's enough. Fast enough to connect galaxies, slow enough to give us time, perfect enough to hold the universe together. So rest now. Let these thoughts settle. Let the geometry of space-time cradle you. Let time flow at its own rate, carrying you gently through the night. The universe has a speed limit, and because of that limit, you exist. You experience. You change. You are. Sleep well. Dream gently. And when you wake, know that you're traveling through space-time, at the speed of life, following paths shaped by gravity and choice, connected to everything by light and time, and the elegant structure that makes it all possible. Thank you for drifting with me, through these quiet hours, for letting curiosity guide you, for exploring the hidden architecture of reality with patience and wonder. If this journey brought you peace, or sparked something in your mind, or simply helped you see the universe a little differently, then it was time well spent. And if you'd like more stories told, softly more science whispered into the night, more journeys through the cosmos and the structures beneath it, there will be more waiting. Until then, good night. Rest deeply. And remember, the universe has a speed limit, and that limit is what gives us time. Time to wonder, time to learn, time to be. Good night.